right here and heckling too. I suppose yeah. So I think we're going to go ahead and get started. Greetings, everyone. My name is Chandler Carruth. Really happy to be here. Actually, really happy to be here. I haven't actually been to Norway before. I haven't been to this conference before. It's so far amazing. I'm really excited about all of it. And I'm here to talk to you a little bit about the Carbon language and kind of our road to 0.1. And I just want to dive into stuff because we've got a lot of material to get through. So let's get started. So first off, what is the Carbon language? How many folks here are familiar with Carbon? They know exactly what I'm here to talk about. Some, not everyone. So Carbon language is an attempt to build a successor language for C++. Now, what do we mean by a successor language? Well, you're familiar with one of them if you've ever used C++, because actually C++ is a successor language for C. Right? That's actually how C++ got its start, was actually being a successor for C. And it's not the only one that you've probably heard of. You might have heard of TypeScript, a very popular language, right, which is a successor language for JavaScript. Now, both TypeScript and C++ took a very specific approach to being a successor language. They kind of are supersets. Right? If you write C code, generally speaking, it is also going to work in C++. I know there's some committee members here. Please don't quibble with the details on this. It's largely a superset, and TypeScript is the same way. If you have good and correct JavaScript code, it just works as TypeScript code. And it's a really effective approach to make a successor language, but it does have some downsides. It means you inherit a lot of the technical debt of the original language, right? And something really exciting has happened in recent years. There's been a different kind of successor language to come out. The first one for me that kind of opened my eyes was Swift. Right? And Swift is actually very much a successor to Objective-C, if you look at it. But in no way is Swift a superset of Objective-C. How many folks here know Objective-C syntax? I'm sorry to all of you. It's a really painful syntax in particular, but a bunch of great ideas. And Swift was able to basically build a really clean, a really nice language, but very much built on the same fundamental ideas of Objective-C, some of the same fundamental ideas of Objective-C. It was a really great successor language, and it did this through interop. You could use all of your Objective-C code in Swift very easily, very transparently. And another language kind of is taking this further, and that's Kotlin. I don't know if folks here are familiar with Kotlin, but it's a successor language for Java. And Kotlin, I think, is just the best example of this because you can use Java APIs in Kotlin. You can even turn that around, and you can use your Kotlin APIs in Java. The two languages play very nicely together. They have beautiful interop, but it is its own language, right? It doesn't include every aspect of Java. It gets to do its own thing. It gets to kind of move past some of the technical debt, and I think that's incredibly powerful. And so our idea is, can we build something like Kotlin, but for C++, right? That's kind of the crux of the idea of Carbon. And what we want to achieve with this is being this kind of a successor language. And so where do we start with that? Well, we start off with C++. We actually start with our specific goals for C++. A bunch of folks wrote some of these goals down in a paper several years ago. We want high-performance software. We want to take care of evolution. We want code that's easy to read and understand and to write. We want safety and testing mechanisms, right? Scalable and fast development tools, right? We, of course, have to support all the modern platforms and hardware and environments. But to be a successor language, we have to tweak these a little bit, because these were goals for C++ itself. As a successor language, we have to add one more, which is around interoperability and migration. Okay, from existing C++ code. And these two things are kind of the whole thing I want to talk to you today about is what do we mean by interoperability and migration? Because that forms the core of kind of Carbon's most exciting promise. That's really what we're focused on, especially going into 0.1, is all about interoperability and migration. Now, since we announced this at C++ North a couple of years ago, you can kind of see the star history chart where we did the announcement 2 years ago. We got maybe a little too much attention from that announcement because Carbon was an incredibly early stage project. I don't think people realized how serious we were when we were saying we're just getting started. We were very serious about that. But it is now a really nice open source project. We've been very active over the last few years, right? Over 1,800 PRs closed, 120 new contributors. We've got a very active Discord server where all of the development kind of discussions are taking place. All of this is open. It's all on GitHub. We're actually kind of obsessed with GitHub. We use GitHub in every way that we can for all of our development processes. In fact, one of our more interesting processes is around governance and evolution. This was probably the first challenge we really set out to overcome with Carbon. And we have a really, I think a really nice, at least for us, nice governance and evolution process. So we have 3 Carbon leads. Kate Gregory, who just gave a talk and is giving another talk tomorrow, Richard Smith, and myself. We plan to kind of expand this with teams and kind of have a nice sharding function as the project grows, but right now it's just the 3 leads for kind of making decisions. And as Carbon evolves, we evolve it through a proposal process. But proposals aren't like weird like PDF processes that come out in a mailing. We have a very, very easy process. It's just a pull request. It's just a GitHub pull request. We attach a special document to it. And that document really reflects the purpose of proposals. Right? Our evolution process is really centered on documenting what's changing and why is it changing. Like, what problem are we trying to solve? What alternatives didn't work out? Like, what's motivating us to do all of this, and why do we think this is the right approach? And these PRs have kind of an RFC period or request for comment period, right? That's open to feedback from everyone, and eventually they have to be approved by at least one of the leads. One of the nice things is we also can roll these back. Some folks have a lot of process to try and make sure that they get all of the feedback onto these proposals, they don't miss anything, that they get it right the first time. We basically don't think we will ever succeed at getting it right, and so we're trying to just plan for some failures, right? We're going to make mistakes here, and that's okay. We can roll things back. We can actually reverse things and change our minds and change our opinion. That's kind of an inherent part of the process we want to use. Now, this process, though, is anchored around documenting the evolution. It's not really a great way to make point decisions. So we have a separate process for point decision making. And these are called leads questions. And these are just special GitHub issues. There's not anything more formal to them than that. You create a GitHub issue, you mark that it's a leads question to get the leads feedback on it, and you start talking about what decision we need to make. These can range from super lightweight process to get feedback like, should we go in this direction, should we look at this thing, to really contentious, difficult decisions. We'll actually extract the entire discussion around those decisions out of a proposal and into an issue. Excuse me. So another thing that we're trying to do with Carbon is have a roadmap to give you some idea of kind of where we're going. It also helps focus the project, keep us putting all of our energy into the things that are really our priority. And it telegraphs to people, some things aren't our priority right now. Right now, we're not going to be looking at these things. If you want to contribute, you'll have to focus on something else. So we publish these at the start of every year, just through the normal proposal process. And it includes a mini retrospective of the previous year. Sorry, I seem to be losing my voice a little bit. Hopefully we'll make it through this. You can find our 2022 roadmap, which really focused on kind of making Carbon public, getting the open source project off the ground. You can also find our 2023 roadmap, which was really focused around defining an MVP or an 0.1 version of Carbon. And we'll get into more of these things as we go through the talk. So for 2024, our theme is really around building a working toolchain. And this is where we are today. We've got it. We've got the project public. We've got an active open source project. We have a definition for kind of the milestones we want to be hitting. We're really focused on how do we make a toolchain. And part of the reason for focusing so much on this during 2024 is we heard a lot of feedback from folks that they really need a working toolchain to evaluate Carbon, to understand it, right? And even to contribute or participate. It felt like it was really holding people back. It made Carbon feel a bit like vaporware. And so this is where we're going to put a lot of our energy this year. And the nice thing is that this is also going to, I think, really unlock a lot of visibility into what it means to have Carbon and what we can do with it. Now, to have a viable toolchain, we need to support building meaningful Carbon programs, and we need to get some amount of C++ interop. And so this is kind of, I think, the interesting thing to talk about. But just so you know, we do have some telegraphs around 2025. If you click, we're going to try and finish our MVP in 2025, get to actually 0.1. And that kind of raises an important question we glossed over, which is, what are we talking about with this whole MVP thing? And what do we mean by 0.1? So, Carbon has a set of milestones that we're using. And these are milestones not in terms of time, but in terms of functionality, right? And these tend to be things that are like really clear inflection points that we can already anticipate. First one of these we're calling kind of version 0.1, which is the MVP, or minimum viable product, for people to start evaluating carbon, right? Not to like ship anything, not even necessarily to finish the evaluation, but to start evaluating it seriously. And this is really going to be focused around complete functioning C++ interop. That's the driving thing behind everything in 0.1. In 0.2, we want to try and get to something feature complete enough that people can actually finish evaluating. They can actually wrap up their ideas about whether this makes sense or not for them, and really make kind of clear decisions. And there are a bunch of notable features that we'll talk about here, but one of them is definitely, this is where we really see memory safety coming into the picture in a big way. And the only other thing that we can anticipate this early is that, of course, at some point, if we're successful, we will like to have a 1.0, right? This is kind of a production quality thing. That is a long way away, though. That's kind of in the distant future. And that's something I just want to emphasize. These milestones are not short-term milestones. We're not going to do this in the next 100 days or something like that. These are multi-year kind of milestones. We're really building for sustainability and for the long term. We're not trying to do anything short-term here. And so with that, I want to zoom in a little bit on this MVP and Carbon 0.1 and talk a little bit in more detail about it. So first off, what do we want to achieve with an 0.1 release of Carbon? So our goal is to enable evaluation of Carbon as a C++ successor, right? And that tells us something right away. Our target audience isn't kind of random developers. They're not new grad developers. It's not all of the developers. It's specifically existing C++ developers. Existing C++ users, people who already have a C++ code base and might be considering moving to a different language. We also need this evaluation to be serious, right? To actually be a credible evaluation of whether Carbon makes sense for them. And that means it has to integrate into a real C++ development environment. It can't be kind of a toy project on the side. It means that they need to build working code, even if they're not going to ship it to production. All that said, we want it to be as minimal as we can get away with, because that's going to let us move more quickly. Like, we don't want to put more things than we need to in here. And the way we really think about the gaps here and keeping this minimal is that these gaps need to be things that don't undermine the confidence of any evaluation people are doing. It's okay if they can't finish their evaluation, but if we have something that's like, well, I can't really trust anything that I'm testing right now because it's all standing on this house of cards that doesn't make sense. That kind of confidence gap is one we do have to care about and we have to really close. And these aren't just like the dimensions around language features. We have a bunch of different evaluation dimensions that we have to think about. From the fundamental language constructs, right? How do you handle generic code? How do you handle control flow? To things like the functional C++ interop. How do you call across the language boundary? We think people are going to care about build speed and scalability. Like, how does it actually impact a realistic, production code base and its build system? And we also think people are going to care about performance and generated code quality. People are going to build actual benchmarks with Carbon as part of their evaluation. We need to make sure that the performance is realistic and, frankly, very competitive. So when we look just at the 0.1 language, I can't emphasize enough that this does need to be minimal, but it's all of the necessary features to support evaluation. And this is based on kind of our current design, our current understanding of the dependencies of all the different parts of the design. We're going to try and hold to that. So if there's something we discover, we can get away without this and still evaluate it, we're going to try and remove that and pare down the 0.1. But we will also add things if we discover they truly are necessary. We have a long list of the current kind of expected features on our milestones documentation. I don't want to just like read a list of language features to you, though, but these are the kinds of things we're thinking about for the language itself. I think the more interesting thing is the fact that there's a lot of stuff you're going to find that's missing. And that may be a little bit frustrating at first when you look at 0.1, you're like, but you don't even have X for your favorite language feature X. And that's intentional. The smaller we can make it, the sooner we can ship it. And so at each point, we're going to look critically and see if we can rip something out. If an evaluator can make progress without that, then it doesn't belong in 0.1. That's something we can bring in later. If it's going to undermine their ability or undermine their confidence, that starts to be a real problem. And we are going to try and hold to this. And that means that I want to kind of talk about some of these things that are not going to make it, and that we've even explicitly deferred to the 0.2 milestone, because I think they're a little bit surprising. And 3 of them I want to call out are coroutines, memory safety, and metaprogramming. There are a few more that you can find in our docs, but I think these 3 are interesting to really look at to understand why we're leaving them out, why they're going to come in second instead of first. So metaprogramming is maybe the easier of these. right? It's not as relevant for interop as you would think. You typically don't have a lot of metaprogramming on your API boundaries. It tends to be something that's more inside of your implementation. And so that makes it a little bit easier for us to not include it when we're looking at an interop-focused 0.1. We're also pretty well versed at avoiding the reflection side of metaprogramming in C++ because most folks haven't had it. It's only just coming into the standard. But the other reason why we really want to leave metaprogramming out is that metaprogramming is incredibly expensive to add to a language. It's incredibly difficult. If we can leave this out, this is a huge, huge reduction in the amount of work to get to 0.1, and so it's really valuable if we can skip it. The only thing we think we can't skip are some really kind of small tactical features. We'll probably have to have conditional compilation to handle different platforms, that kind of thing. But we want it to be as small and tactical as possible because otherwise we're kind of opening an enormous can of worms that we don't need to for this version. Coroutines is another example that's, I think, tricky and a little frustrating. This one's actually really frustrating to me because I particularly like coroutines as a language feature. I think it's so powerful. But it's also incredibly complex. Adding coroutines to our scope would set us back an incredible amount of time. And I think it's interesting to see that both Rust and C++ are still actively learning about how coroutines work in their language. They're still kind of firming up their understanding. We're seeing talks throughout this year of people about like, I've figured out a thing about coroutines. And that means that I think we can actually very usefully wait here. Right? We can actually, help these folks learn. We can kind of learn more about how to use coroutines well and reflect on that and actually incorporate that into Carbon when we get around to it. We're also really confident that we can evaluate things without coroutines. We've been using C++ without coroutines for a long time. We're very familiar with it, and a lot of code doesn't need coroutines, and so there's lots of places you can still evaluate here. Memory safety is maybe the toughest call. I know not everyone likes to care about memory safety, but I do think it is incredibly important and maybe the most important thing for kind of programming languages over the next decade or two. And it's really frustrating to not have this here. But I want to be very clear about why. Very fundamentally, C++ is memory unsafe. It is fundamentally a memory unsafe language, and there's no way around that. And it's not going to become memory safe. There is no credible, realistic path to C++ becoming memory safe in the future. And so the fundamental reality is that any Carbon interop with C++ is going to be interoperating with an unsafe language. And the Carbon code on the Carbon side of that interop is itself going to be unsafe. You see that in every language that does interop with C++. There is some amount of unsafe code you simply have to write. And so that really needs to be our priority for 0.1. If we're focused around interop, we need to get the unsafe layer of Carbon right, because that's going to be the foundation for the interop into C++. That doesn't mean that memory safety isn't a goal or isn't important. It is incredibly, incredibly important. It is going to be one of the most important things we work on. But it needs to be something we can layer on top of unsafe code, because we need that unsafe layer in order to interoperate with C++. We have to meet C++ where it is there. So with all of that, I want to kind of shift gears from talking about exactly how we define 0.1 to more like where we're trying to get to. Like what are we trying to build towards with 0.1? What direction are we moving in? And what's the end state going to look like? And what should we be kind of evaluating for in that end state? So that means I need to explain Carbon's kind of incremental migration vision. And this isn't something we've really had a good set of chances to talk about, but we have a very specific idea for what it needs to look like to migrate from C++ into Carbon. I'm going to try and walk all the way through that with you today. So first, we have to meet C++ users where they are, and fundamentally, they're C++ users. They're using C++. So that's actually where we start. The first increment of Carbon's migration isn't Carbon at all. The Carbon toolchain is actually going to provide a drop-in C++ toolchain for your C++ code. And that's actually the very first thing we want. We want to package up Clang and libc++ and LLVM and all of the different components into a complete, really nice, really well-packaged C++ toolchain that you can just put into your existing build system, right, and use to build your existing C++ code. Right? And our goal is really, if you can build your C++ code with Clang, you should be able to build it with Carbon's toolchain because it's just a packaging of Clang. And the first incremental step of trying out Carbon is actually to switch your build to Carbon's C++ toolchain, right? Which should be fairly straightforward. You don't have to change any of your source code for that. And we think it can even give some nice benefits, right? Currently today, it's actually really annoying to get a stable, but also really up-to-date version of a Clang-based toolchain. And we can kind of solve that. We can make it a lot more approachable. We can also make some of the more advanced features a lot easier. Things like getting all of the runtimes, like libc++, but not in the shared form, actually in the archive form, so that you don't have to get your R paths right. If someone has ever fought with libc++ R paths before, I feel your pain. I don't know if folks even know about the LLVM libc project, which is a libc overlay being developed in LLVM with some really, really fantastic optimizations and performance improvements in it. But almost no one uses it because it's really hard to actually get it and install it and like configure your whole build system to use this feature. We can kind of automate that. We can make it really, really easy for folks. And so I think there's some advantages we can bring here. Long term, one thing I really want us to do is to make sure we support not just one operating system, but Linux, macOS, and Windows. Clang is a really unique toolchain because it actually has really strong native support for all of these operating systems, right? You can actually build C++ code on all of these operating systems with it, and that's something that we can enable by kind of packaging it and making it more readily available. Okay, so once we have you using our build system, our tool chain, we can take the second increment. And the second increment is basically our hello world. This for me is what hello world is for a successor language, as opposed to kind of for a language that stands in isolation. Or you want to take one typically very small C++ function in your code base and move just that one function over to Carbon, right? So you add, one Carbon file to your existing build system, right? You don't have to change any of your build system, just one new file, right? You're already using Carbon's toolchain to build all of your C++ code, and Carbon itself will have the same fundamental build model as C++, and so whatever your build system does for C++, that'll work for Carbon, right? You need to use some existing C++ APIs from this function that you're moving, so you're going to have to call your C++ code. And of course, I hope you're not moving a dead function into Carbon. You're moving one that actually has users, and so you also need the function you move into Carbon to be available to the rest of your C++ code, right? And so this is kind of the first real test of Carbon from a migration stance. So let's kind of illustrate what this looks like. So we have some lovely, everyone's favorite C++ code here, right? We have, a function that provides the hello string. We have a hello world function that kind of takes the hello string and puts the world onto it. We have our main function that calls the hello world function and gets the string. So this is our C++ code. We want to take this first step. So we're going to take this hello world header file and source file, and we're going to create a hello world.carbon file, right, and move one function into it. And we kind of know what things to put in this file, right? The hello world in C++ was in a greeting namespace. Carbon files are all forcibly in some top-level namespace. We actually call it a package, and so we'll call that one greeting here. And we know that there's a function called hello world, so we'll put the hello world function in Carbon's file. It returns a string in C++, so we'll need to return whatever Carbon string is. I don't think it'll actually be spelled core.string here for what it's worth, but we don't have a decision on exactly what the spelling is, so I use kind of a safe, some string type in our standard library. Right? And it's going to do the code in the Carbon side is going to look fairly similar to the C++ code. It's going to get the start of the greeting string. It's going to append the world part of it. Right? It's going to return it. But there's some challenges here to doing this. Right? The first one is we have to call hello somehow, because hello is still in C++. We didn't move that one. So that still has to get done. And we also need to somehow include a header file into the code with the main function, right? And access a function and call it and get a string back, right? So those are the pieces that are really missing. So let's just kind of continue down into the rabbit hole for a bit and see how this actually ends up working. All right, so we want to, first off, import this hello function in C++, and we're going to do that by actually using Clang, right? Because we need to access this hello function. So we've got our Carbon file. We're going to add an import of a C++ library with a header name of hello.h. Right, so you can just directly import C++ headers into your Carbon code. Now, what's that going to actually do? Right? So I'm going to kind of illustrate what we're going to implement inside the compiler using source code. This isn't actual source code that anyone's ever going to write or see. Just think of these as like whatever your internal compiler data structures are. This is a source code way of visualizing it. So Carbon is, so what we're going to do is we're going to ask Clang to build a C++ module, okay, C++ 20 module, that's going to represent the APIs available in this header file. And the way it can do that is that there's this really cool feature inside of C++ 20 modules called header units that I know a lot of people really don't like. I'm sympathetic, but also it's incredibly important because it lets you do this cool trick, which is it lets you actually take some header file and say, go find everything in that header file and export it from my module. Right? Now, when you're actually implementing C++ 20 modules, this means you have to be able to walk all of the APIs from that header and actually serialize them into some kind of module. That's not the use case we have for it. What this is going to let us do is have the Carbon toolchain go through all of the APIs that show up as part of exporting hello.h and build interop for them. And so the Carbon compiler is going to go and build, again, this is not real code, it's going to go and build some synthetic code to model interoperating with the APIs that came from hello.h. Right? And so this is in the package CPP because we want to try and have a layer of safety from C++, which has a global namespace. We don't have a global namespace in Carbon. But we can go through and like, well, this file has a namespace called greeting, so we know to put a namespace called greeting into the Carbon API, right? It has a function called hello, so we can put a function called hello in the namespace greeting in the Carbon API. We know that that function returns a std string, and Carbon can kind of model whatever type mappings need to happen. It's like, well, okay, when you're calling this function from Carbon, we should remap the standard string type of C++ into Carbon string type, and so I'll return Carbon string type on the Carbon side of this API. Right, so this is basically the synthetic thing in the Carbon compiler that the API is going to expose from this import, right? So that you have kind of all Carbon-based things to interact with in your Carbon code. Right, so inside the Carbon code, you can now just call this CVP greeting hello. That's no problem at all, right? And we know what that is because we kind of built it, right? And when you do, inside that implementation, right, it's going to have to somehow get back to the C++ side of the world. And it's going to call this implementation detail function call greeting hello, right, that users never touch, never write, never have to see, right? And then that's going to go and call the C++ hello function, right, which is going to return a std string, which is going to get returned through the kind of internal magic one, right? And it's going to show back up on the Carbon side of the world, still as a C++ std string. And so there's one other thing here. We had that type mapping. We actually have to do something to the string to kind of get it back into the right type, right? We need to get it back into the Carbon string type, and so we have to do a type conversion. We can imagine that, you know, Carbon string type is hopefully built for a really nice convertible back and forth between C++'s string type. All right? Now, there's some important details here that I just want to emphasize, and that's that when we had a call to the C++ function, the C++ hello function, we didn't do that actual call in Carbon, right? And that's important. We actually did it in C++, right? Because this means that we don't need to have all of the C++ rules mirrored into Carbon, right? This is just a C++ function call. It has ADL and overloading and implicit conversions and, you know, array type decay and function type decay, all kinds of fun things and really bizarre rules that we never need to think about or put into Carbon because we actually do the function call on the C++ side of the boundary. Right? We connect these two with this magic implementation detail function. This is all synthesized by the compiler, and it controls both ends of that. And so it can arrange for that to be simple and boring and easy to move back and forth between the languages. Right? Anything that's really Carbon specific, anything that's really C++ specific, and especially anything that users are interacting with, we keep wholly on one side or the other. We don't let it bleed across. Right? And that's kind of how we can manage the complexity of both languages across an interop boundary. Making some sense? No questions. Everybody's still good. All right. So now we have to turn it around. I'm sorry?
Yeah, still here.
We're still here. Excellent. So now we have to turn that around and call C++ from Carbon. And it turns out this is in some ways easier. So again, the bottom code, this is not real code. This is just synthesized code for you to understand what's happening here. But now we have the main function in our C++ code, and we have to do something really weird. We have to include a header file, right? And that's a little exciting. But remember when I said that we got all of your C++ code building with the Carbon toolchain, right? That was important. That wasn't just like an incidental thing, because that means this isn't just the C++ compiler building your C++ code. It's a C++ compiler that knows about Carbon. And so when it sees an include of this header, it can know, hey, wait a minute. You're trying to access Carbon code. And it can synthesize the header file you would want to have in order to access that Carbon code. Right? We can build up whatever header file kind of formulation would allow your C++ code to reach into Carbon, right? We know what to put in that because we can go and walk through the Carbon file, and it has a greeting top-level namespace. We call it a package in Carbon, so we'll put a top-level namespace of greeting into the C++ code. Right? It has a function called hello world inside that, and so we'll put a function inside it called hello world. Right? And that means that once you go back to C++ code, I got normal C++ things. I got a greeting namespace and a function called hello world, so I can do a using declaration of it, no problem. I can call it, no problem at all, right? But when I do call it, in the implementation of that header, it can reach into something magic, right? Different kind of magic, but again, we're going to go to magic. Some C++ exporting wrapper thing, right, which we put in our own special weird namespace, or however we want to set it off from everything else. Right? And it's magic. This is, again, a compiler synthesized and controlled boundary between the two languages. And we can go over into the Carbon side, and when we're implementing this package, we can synthesize some extra generated code to support the C++ use case. Right? We can generate our magical function that maps this Carbon function into the C++ world. And the nice thing here is that in Carbon, we can still talk about the C++ types. Right? We just covered how we import things into Carbon from C++. So we can talk about the C++ std string and the fact that we are going to have a type conversion. We want to handle that type conversion in Carbon where we maybe have more capabilities. We may have written some special type conversion rules for it. And so then we can kind of call the pure Carbon function here in Carbon. Right? We get the Carbon string, and we can handle any type conversions or mappings or whatever is necessary to make it kind of ready for the C++ world before we hand it back. And it shows up as a std string, right, which gets returned from our little wrapper and shows up into the C++ code. Making some sense. Right? And so this lets us, print hello world with interop. Right? It's easy, no problem, right? Ship it. Not that easy. So this is actually really hard, but hopefully this helps you kind of understand what we have to do. And the nice thing for me is that this pattern generalizes really well. We can extend this systematically for each and every feature in the language that can show up on an API boundary. And this is what forms the basis of our kind of fine-grained interop story. Every piece of C++ functionality we need to send across an API boundary, we do something roughly like this. We build all of these little stages, and we actually can move that across the language boundary. Right? And our goal is that you should be able to move one construct across the boundary at a time if needed. Right? And if you want to see some really complex examples that go all the way through virtual functions and templates, I think, in a talk I gave at CPP Now last year. Lots of fun examples in there. But users probably aren't going to migrate one function at a time for very long. I mean, sure, maybe that's your hello world. You try it out, make sure everything works. But you probably are going to have a different unit of migration. And we expect the typical unit of migration for users to be basically one, what we call modular header files, okay? And so a modular header is basically some entry point includable header, like a header that you actually tell people, yeah, you include this if you want to get at my API, right? As well as all of its implementation details, any implementation detail header files or sources, whatever all the constituent parts of it. In Carbon, we tend to call this a library. It's our minimal importable or in C++ includable unit of API, right? And that's kind of the granularity we expect people to really want to migrate on, because that's going to be the one that fits naturally with how they've organized their code already. And the other thing is you probably don't want to have some library of code and its unit tests split into two different languages. I don't know about you, but that would not make me happy. So it'll probably also include all of the unit tests for it. But there's an interesting thing here. While that's the granularity of migration you want to kind of maybe submit to your code base, there are some increments within that I think provide really, really interesting process. Right. Also, a brief tangent about C++20 modules. I know I'm talking a lot about header files. Yes, we know that modules are out there. They're wonderful. We're definitely going to support them the same way as header files. They should really work very similarly to modular headers in terms of how we use them. The only reason they're not our focus is because there's just so many header files in the world. We have to make sure we have a really good story for the header files. We are designing all of this so that it integrates with C++ modules. However, this brings up another tangent. I'm sorry for kind of the repeated tangents here, but also C++ modules kind of tempt people towards these umbrella modules like import std and things. That's going to present some real challenges. They're going to work, but I think they're going to be less efficient. And this has nothing to do with Carbon or Clang or anything else. This is about build systems. Umbrella modules really limit your build parallelism if you have a lot of them in your code base. They can also be very expensive to serialize. I just want to say, generally, I advocate to have kind of the smallest unit of importable API that makes sense, not the largest. Just personal preference. I think that's actually would be really nice if we could move towards narrow units of import and fine-grained dependencies, because it really helps kind of build systems kind of maximize their parallelism, maximize incremental rebuilds. Anyways, okay, I'm sorry for the tangent. We're going to get back to topic here. So, incrementally migrating a library is going to have some stages in it, right? It's not going to happen all at once. The first stage is you're probably going to migrate the header and its implementation files from C++ to Carbon, right? And hopefully we have really nice tooling that targets that kind of even, you can point it at a header file. It's like, oh, so that header file has these implementation headers, and these source files, we'll migrate those together. Does that make sense, right? And we can try and produce something that's really near complete, nearly idiomatic Carbon code from C++ code. Right? Carbon's designed to have good matching with C++ idioms. Right? That's one of its points. And where we have kind of improvements or things we'd like you to do better, we can have heuristics to try and lift from C++ idioms into kind of nicer Carbon idioms. But we're going to have reasonable fallbacks for almost everything. Right? And very rarely, we will leave like a fix me comment to be like, this is super ugly. I don't know what was going on in the C++ code. We did the best we could, but you should look at this code and make sure it's actually working the way you want. And even when we do that, we'll try and actually come up with some contrived sequence of Carbon code that precisely replicates the behavior of the C++ code, if we can do so. I mean, maybe there are some cases where we can't, but generally speaking, we expect to be able to just like it's more that this is going to need eyes and code review, not that it's going to completely fall apart. That's the kind of experience we want people to have here. Now, notably, that's not going to move the unit tests at first, and that's a really exciting thing, because with Carbon, we can re-export that C++ API that we just migrated, now from Carbon, and we can run the existing C++ unit tests against it and make sure that the migration didn't change anything, didn't break anything, that we actually got it right. And if there were problems with it, you can kind of iterate there with your unit tests, like unchanged unit tests. You know that you didn't break the unit tests. You can iterate until you're really happy with the Carbon code that came out of that migration, right? And only once you're really happy with it, then you can kind of migrate the tests and keep the library code the same, and get the test to be what you want in Carbon, right? And so we actually want to support this kind of two-stage migration, and the bidirectional interop is so powerful for this, because it enables you to really reuse your existing tests to check that your migration is actually working. And so once you have this process, you can kind of rinse and repeat, right? Every time you have a library you'd like to move to Carbon, you go, you run some tooling, it moves the library, you check any comments or fix-me's that were left in it, right? Once it's good, you migrate the tests over as well, you land that, and now you're in Carbon, right? And you're able to do that kind of anywhere in your code base, independently of how other parts of the code base are migrating. This is kind of the vision for how we want carbon migration to work. So I'm sure everybody's wondering, when do we get to try this out, right? Sadly, not yet. We're not quite to this yet. In fact, I want to remind folks, this is our vision for incremental migration. We're not going to have all of that in O.1. There's no way. There's just no way we can have all of this in O.1. And our timeline for reaching O.1 isn't tomorrow, I'm afraid. I wish we were here to announce O.1. That would be really cool and all, but we're not quite there. So we have a stretch goal of finishing O.1 next year. We're really going to be closing in, I think, throughout next year. The toolchain, the language, and the interop support you're going to see in Carbon are going to be very steadily expanding over the course of the next year. I think probably packaging up the C++ toolchain and kind of making that package C++ toolchain available is probably one of the first things that's going to land relatively earlier in the year. But getting all the way to O.1, I think, is a bit unlikely. It's a bit of a stretch goal. I think there's just a lot of interop and a lot of dependencies of interop in the language that we're going to have to sort through in order to finish O.1. Of course, the thing that always helps us is more contributors, but we're making pretty steady progress at this point, and I think we're going to get there, if not in next year, very shortly after. But O.1's not going to include all of this lovely automation, right? The vision is really just a long-term vision. Good tooling and good automation for this kind of migration is its whole own incredibly large project. But we think we can evaluate without that because we can just do some of those steps more manually. And we can provide at least rudimentary tools to help with the most mechanical parts of this. I don't want anyone like updating keywords from one spelling to another. We have scripts and stuff for that. But to get to the really high quality tooling, I think is going to take a lot longer, and I don't want people to be surprised. The first few versions, hopefully the interop part of that migration story works, but maybe all of the other things are quite rough edges. So why is it taking so long? So look, things have not been purely smooth sailing on the Carbon project. I wish they had. I wish I had no problems on the horizon. It turns out designing a generic system that supports C++'s use cases is incredibly hard. You have to have basically all of the most difficult things to put in a generic type system, from specialization to templates to open extension points. It's incredible. And we want to do that without kind of reintroducing things like undiagnosed ODR problems or the sound issues that plague most other type systems. The other thing that was really hard is actually building a working governance and evolution model. It turned out that took us a whole bunch of attempts to get right. If you want some of the fun stories, ask me or Kate anytime. We have many scars to talk about how this was not obvious at first. Also, I just have to say briefly, starting a new programming language right before a global pandemic is not ideal. That was not great in the way of planning. Didn't really plan for it, but that definitely was a wrinkle. Like, lots of stuff has gone wrong. At a higher level, though, we're not trying to race forward with Carbon, right? We're trying to build Carbon for the long term. We're trying to really get the foundations right. We've seen deferring kind of foundational work cause problems for C++, cause problems for Clang over and over again. We never end up going back and actually refitting and fixing problems in the foundational work. Everything ends up building on top of them. There are too many dependencies. We give up and we live with the kind of messy foundations there, right? We're really trying to prioritize these foundational improvements. We're also trying to set ourselves up for sustainability and for the long term, even at the expense of speed in some cases. The thing we are trying to do is we're trying to recapture speed through incrementality wherever we can, right? And so this is why we have the more minimal O.1, because that gives us incrementality for speed. We don't want to cut corners and have kind of shaky foundations in O.1. And the investment in the foundations is actually paying off. There's a lot of cool stuff we're starting to see where these investments are actually bearing a lot of fruit. And I think it'd be really nice to kind of look at one and make it a lot more concrete, specifically this tool chain that we've supposedly been working on all year. And I think rather than do that on slides, we should do that live. Live demo is perilous, and so we'll see how this goes. But we're going to try and do a little bit of live demo. So the first bit of live demo is, this is just the Carbon GitHub. There's nothing special here. Like, And if we go to the whole getting started thing, we have a new bit of text here that's really exciting if you haven't seen it, because we are actually putting out nightly builds of the Carbon toolchain that you can just download and play with. And we have a bunch of steps to do that, but copying and pasting stuff is lame and not very much live demo. So I'm going to try and actually live demo this. So I don't use bash, I use the fish shell, so it doesn't look exactly like the script. But we're going to set a version to yesterday's date. And sorry if I'm a little bit awkward typing here because I have to do this on a Linux machine that's not up on the podium. So we have yesterday's date. And now we can kind of go and download a snapshot of the toolchain from the kind of nightly builds that we put up on GitHub. So we'll go and hopefully download stuff very quickly. Oh, goodness, quick. And we can extract that and just go into it. We've got a lovely compiler here. And run it. It has help. It has lots of help, but you'll notice that the line wrapping is really bad, and they're like to-dos. I mentioned we are doing incrementality, so there are plenty of to-dos. If anyone wants to work on detecting the terminal width and line wrapping our help output, please don't. There's much more important stuff to do. But we also need to write some lovely Carbon code. So let's write a little bit of Carbon code here. Some function that's going to run, and we're going to call a print function, print 42. Come on. I love having lots of lag. So it's a delightful Carbon function. And we can try and compile this function. We can say where we want the output. But I can spell it correctly. Right, it compiles. We can even link it. Like so. And maybe we can even run it. And it prints 42. So we have an actual toolchain working. It's not bad. But 42 is maybe the answer, but also not that exciting. We can do better than this. But I'm not going to keep doing this with lots of high latency. I'm going to make things a little bit more interesting. So we also have a really cool example that you can look at. And so this is everyone's favorite programming language example. It's a prime sieve, right? Prime sieves, if folks don't know, are great programming language test cases because you have to have a Turing-complete language to build a prime sieve. But you only have to have a Turing-complete language with integers to build a prime sieve. And that really helps because it means you don't need the rest of the standard library. And to give you an idea of why that's really important, because again, the toolchain is not at all finished yet, I can scroll up in this example, and you will see that, in fact, our integer support from the standard library is inlined into the example code here because importing of the standard library things doesn't quite work anyways. This will eventually be in the standard library. But we have a prime sieve, right? It has we have factory functions in Carbon instead of constructors. And so this is just a factory function that returns a sieve object. And we have a to-do here because we don't have for loops yet. We only have while loops. And we have a loop that sees if it's prime, increments the counter, returns it, right? It has all the rest of the code here, right? It's pretty nice. And let's see if we can actually run that. So this is on my laptop, and this is just a checkout of the Carbon toolchain. If you just go and you download it and you follow our instructions to install all the dependencies here, then you can just run. So we actually use Bazel as our build system. I know it's not our favorite one. That's just what we're using. We're going to support all of the build systems, of course. But it does let us do really cool stuff. For example, we can actually build the toolchain in the host build of Bazel and then use the toolchain to build our example code. And this is going to do that, and this is going to do it live, and so this may actually not be instantaneous. I don't know if I have a cached version of everything here. Nope. I have some in-flight code that doesn't work. Let's try this again. also more cache, which is great. So this actually builds the toolchain, and it's going to use the toolchain to build that Carbon code, and then it's going to run it, which takes a little bit, and finds the first, all the primes below 1,000, right? And this is a real code, so we can just, if we run it ourselves, it works just fine, but that's not too exciting. We can do more exciting things than this. So what I'm going to do is I'm going to actually take LDB and try and run this under a debugger. Now, I probably need to set a breakpoint, so, where'd my code go? That's not the right one. That's the right one. So we probably want to set a debugger somewhere. Let's set it on, say, line 91. And run this under the debugger. It runs. Actually stops on that line in the source code. Even prints the little snippet. And we can go to the next line, go to the next line, right? It's almost like a real thing. But let's do something really interesting here. We can step into this. I think we can step into this. Come on. There we go. And so this is going to step into some Carbon code. And this is one thing that I think is really interesting about Carbon's design. A lot of the things that other programming languages have like built into the language, like integers, in Carbon are actually part of the standard library. We have a principle in Carbon that all of the Carbon APIs are library APIs. There's not some magic secret card the Carbon compiler gets to pull out and be like, haha, I have a special kind of API for this data type. Everything is a library. If you write a library integer type, it can have the exact same API as the standard integer types can. And we make good on that by actually having the standard integer types implement the API in library code. And so this is an implementation for the I32 type of a standard library interface in Carbon. And in Carbon, interfaces are the same things as traits in Rust, or as protocols in Swift, or as concept maps in C++ OX. They're basically an abstract description of the interface that you can then implement, right? And so this is the increment interface, and we use that interface whenever we see plus plus on an I32, right? This plus plus I32 to an I32 object actually dispatches into this generic interface implementation for that operation. It's really important for generics in a language because you might want to say, hey, I'm writing generic code and my type supports incrementing, right? And there's actually a way to do that because increment is actually implemented here. But we can also see that we have the implementation just right in line here, which is probably unsurprising. But well, what does plus equal do? We can step further and we can see that add a sign is also in the standard library, right? And that's going to do plus. We can step further, I think, maybe. No, that's as far as we get to step right now. The source locations are a little bit wonky here, but we have like a working toolchain that actually builds a prime sieve. We have some amount of like line-based debug information. You can step through it interactively in the debugger. This is actually like starting to be a little bit more real. The next things are to try and get the rest of the generics kind of core landed so that we can write kind of a correct version of standard library types and to really start diving into C++ interop. But the toolchain is starting to get real. And before I do anything else, I really just want to do one other thing here. We talked in some other talks about how fast the compiler should be in Carbon, and I wanted to just give kind of a live demo of how fast it is. We'll see if this finishes in time. We may have to come back to this as a coda. My build did not have enough cached. Wait. I think this one might be more cached. Maybe? No. Well, I don't want to make you all just sit here and watch me wait for this build to finish. But I promise you the compile times are amazing. That said, this is still early days. It is starting to get more real, but we are still in early days. And mostly, we hope you all want to come and join us on the road to O.1. I think it's going to be really fun. And I think that, we're starting to get something that people can kind of sink their teeth into and be a little bit more exciting. That said, whenever it makes sense for you, I understand this is still very early days, but we'd love to kind of have more people participating. So with that, if folks have questions, and after questions, maybe my build will have finished, and I can switch back to some fun benchmarks. Questions? Anything? Yes?
One of the main selling points of the Carbon is that interoperability with C++ and migrating from existing C++ code base. But will Carbon also try to position itself as a language for new projects, writing from scratch, like compete with Rust? Or
I'm sorry, that last thing, is Carbon trying to position itself?
as a language for the new projects written from scratch, or is it mainly for transitioning existing code base?
So the question is Carbon positioning itself for new projects, or is it really mainly for existing code bases? I mean, I hope that Carbon is useful for new projects. I'm not sad if it works well, and certainly eventually that's going to be relevant. But in terms of our priorities, the first priority is getting it working for existing C++ folks, right? And that's really because that's who's going to be evaluating it, and that's because where a lot of the code already is, and we think that's important. Once that's in great shape, I would love it if Carbon is also really useful for kind of brand new projects, but we kind of have to start with the interop side of it. Other questions? This is the end of my talk, unless my build finishes. We'll see how long it takes. Anyways, yes?
Yeah, going more into specifics, we were talking about the operator plus plus, so the incremental operator
Yes.
implementation. So this goes really through multiple layers, basically. How is kind of the story in your head about making this so fast in terms of build time?
Yeah.
Because does it need compiler knowledge or magic to actually make it fast?
I really wish that this would finish faster. Speaking of slow build times, because it's slow because it's compiling C++ code, specifically LLVM, which is really slow. So the question here is I had this integer arithmetic is going through multiple layers. What is that going to do to build times, to compile times? If that's part of the goal of Carbon, how are we going to cope with that? We think we can do a really great job. So we're modeling it right now very strictly and very formally, where it's like going through all these different layers. We don't expect that to really last. We expect to actually have the compiler kind of intercept and be like, yeah, I've checked that you have all of those nice interfaces and you did all of that dispatch, and here's a built-in implementation that's very fast. And the validation we don't think is going to be slow. I don't know how to say this. The compiler is very fast. If this finishes, I'll show you how fast. It does not. This is not the thing that's going to hurt build times. Not worried at all. Yes.
Will it be possible to have interop with like pre-C++ 20 C++?
Is it possible to have interop with pre-C++ 20 C++? Yes, absolutely. Almost all C++ is pre-C++ 20 C++. Basically, if Clang supports it, we should have interop with it. Like that's really the long-term goal. What we prioritize within that is just based on what is out in the world, right? And so if the world's code bases are mostly in C++ 14 and 17, then that's what we've got to support, right?
So I think what I want to say, Carbon looks really freaking cool, and I definitely want to play with it. But also, I'm curious if you have plans for like automatic header generation and kind of basically, if I'm going to write a library in Carbon, can I expect it to be fairly simple to just ship somebody an SO or a DLL, and they get a header and a DLL, and they can be happy, and it's in Carbon.
So the real question here is, right, like, Can we synthesize? So I had that synthesized header file in my whole interop slides, right? Could we ever get to the point where we actually have one of those and we ship it alongside maybe precompiled code in a binary to users? And I assume part of this is because maybe the users don't even know that there's carbon internally. Absolutely, I think that's something we definitely want to support. There's some tricky parts of that, though. When we're synthesizing that header file, if we want it to be something we can ship to other users, we have to pick a very challenging level of the magic for kind of connecting back to the carbon code, right? Because you have to be able to emit that into something that any C++ compiler it comes across that header will lower correctly. And that might be inefficient, and there might be a few really extreme edge cases that we can't support in that model, where there's just no way for us to express in a header file what you actually need to do. I think those are going to be really rare, though, because we can do stuff like generate templates in that header file. We can do all kinds of special tricks in the generated header to try and minimize that. But there's going to be a limit there. I don't think we can promise quite as much as when we control the actual C++ compiler as well.
And then the other question I have is kind of about like linking model. Like, will I be able to kind of do the nonsense that you need to do in order to generate good DLLs on Windows, for example?
Will you be able to do the nonsense that you need to do to generate good DLLs on Windows?
Like DLL export, DLL import.
Things like controlling export of functions, basically controlling exactly what functions that DLL actually exports and get imported into other DLLs. Absolutely, like we're going to have platform-specific extensions just like DLL export and import to model those inherent platform properties and allow people to develop properly on Windows. I mean, that's a long way away. That's probably something that only is going to manifest when we're really talking about getting into production. But I think that's something we can and should support. Right? That goes to supporting modern operating systems. Right? We can't leave those behind. Will Carbon be able to interoperate directly with C, or will you have to go through C++? I fully expect we'll be able to interoperate with C. Exactly how we implement it, I'm not sure. I mean, Clang doesn't care to a certain extent, and it's all going to go through Clang. And so the difference may be fairly minor, but yeah, it should work fine. Yes?
So similar question, so the integer arithmetic and everything goes through multiple layers of operator calls. Does that mean the runtime performance of debug builds are going to be terrible because it has to call 3 functions?
Question is, does the layers of integer arithmetic mean that debug build runtime is going to be terrible? No. The fact that I could do that in the debugger was just coincidence and luck of the fact that we haven't done any kind of tweaking of this. I would never expect that to be what we actually want to have even in a debug build, because it would just be intractable. No. It was just a nice trick that I could happen to do with the sieve that we already have checked into our code base. We need like 3 more questions? I don't know if we're allowed to go this far over, but I don't have anywhere to go. So, Kate in the back. Yes, thank you. Thank you for reminding me. And so if you didn't like the way I downloaded the toolchain and installed it in like 2 seconds and didn't talk or explain anything in the process, Kate Gregory actually has a course on Pluralsight where she actually walks you through all of this. And it also does it on Windows using WSL. And you can actually see exactly how to do this. For the record, it works on basically any Ubuntu-ish, Debian-ish Linux, including Windows. The WSL, the latest WSL works great. You should totally check that out if it's useful. And we have another question. Someone's on my side to get through. So what happened, for the record, is that one of my delightful colleagues updated our snapshot of LLVM to a new version, and I didn't notice that. Anyways, yes.
What is going to be the story around non-Web C++? Will I be able to use this on Windows with MSVC STL? Will I be able to use this on Linux with new hosted C++?
Sure. So there are 2 sides to this question. So one of the questions like, are we going to be able to work on different operating systems? Windows, Mac OS, Linux, right? They have different environments, all kinds of different constraints. One of the really nice things is that Clang works on all three of these, and increasingly libc++ also works on all three of these. Even on Windows, libc++ is slowly gaining a little bit of Windows support, and we actually hope that that kind of platform support is going to be a really useful horizontal. A separate question is, what about when you don't want to use Clang or you don't want to use libc++? That's a trickier thing because really when we get you to kind of use the exact toolchain that we're shipping, we get to do a lot of really nice cheats to make things work better. I think we have to have a mixed toolchain model, right? We're going to have to support other compilers and other standard libraries, but I think that the level of support is going to drop. For example, we might not get automatic type rewriting. So stood string in MSVC's STL and in the GCC STL might not automatically become the carbon string across interop. It might stay in C++ land. But now my compile time benchmarks are done. Thank you for helping us out there. And I just want to point out, so originally when we announced Carbon and the toolchain in particular, I set some very ambitious goals. I wanted us to lex and parse at 10 million lines of code a second. And I want us to do semantic checking at 1 million lines of code a second, all of that on a single thread, like not using any kind of parallelism. And I just want to point out that we are currently hitting my goal. This is 1.28 million lines of code a second. I actually have some improvements that'll push us over 1.3 and get us close to 1.4. But just to be clear, this is syntax checking. So I have a version of this 4,000 line file that's also generated for C++, and I can run Clang over it. And I don't want to say that it's slow because it's not. It's actually quite fast, like 180 milliseconds. But if I run, and I don't know if this will work. It works. But Carbon's is a little bit faster. So Carbon is more than 10x faster than Clang for something similar. And this is not like trivial code, just to be clear. So what we have here is a bunch of classes. There's 4,000 lines of classes that is automatically generated with all kinds of methods and types, all kinds of fun things here. There are pairs, so we're doing a little bit of template instantiation, but like only pairs. And the Carbon code is exactly the same, right? All of this is generated so that's exactly like apples to apples, as close to apples as I can get. Right, but the comparison is really, really stark. And it only gets, like if I make the files larger, the gap widens here. So we're doing really, 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 really well on compile time so far. Super, super excited about that. So with that, I think we're way over. Thank you, everyone. And you should go try out Carbon.